We now want to look at what we call resisted motion, and basically what we're doing is adding some more resistance to our motion and getting harder functions to use and integrate. So it takes a little bit of more work than we did in the Extension 1 course. So what we're expecting to see with this is looking at equations of motions of particles. They're moving vertically upwards, so later on we'll do downwards, but upwards in a minute. They've got a resistance R which is proportional either to the first or second power of its speed. So it's the proportion is either the first or second power of its speed, so in relation to v. So what we need to be able to do is derive expressions for the velocity in terms of time and velocity in terms of displacement, and also we can get from those the expression for the displacement in terms of time, and also then solve problems using those expressions of acceleration, velocity and displacement. So what can we start to expect? Well, we can only look at cases where the resistance is proportional first or second power. What we should do all the time is put the place of origin at the point of projection, so where it's projected. We also get a maximum height reached by the particle, which can be obtained for expression relating speed and distance, and the time taken to reach the maximum height will be from the expression relating speed and time. A little bit obvious, but that's okay. And problem should in cases where the magnitude of resistance is given as well. So our first case we want to look at is where we've got the motion that's upward in the resistance proportional to the velocity. So what does that basically mean? Well, this is what we're looking at. Your resistance and your mass times acceleration is projecting upwards, so it's being projected upwards. But what we've got resisting it, we've got mass times gravity and mass times something proportional to velocity. So the first power times velocity there. So that's what we're looking at. So by Newton's laws, we know that we have these two opposing each other. So that if in any situation, these must be equal to each other. So that's where we get our equation, our motion, and we start off with that. So acceleration is going to be minus g minus kv. So the first part we want to do is find the vertical displacement of x. And so we're relating x and v together. So to do that, we're going to change the acceleration. We're going to use the v to v dx. Again, you could use the d dx of a half v squared. When we play around with this one, we get the minus g plus kv over v, and we want x in terms of v, so we'll take our reciprocal, and so we get minus v on g plus kv. So x is going to be the integral of minus v on g plus kv. So we need to look at that, and we can see we're going to get a log function, but also when we look at that, the v is the same power there, so we can do some polynomial division because it's the same degree. So we can either do the polynomial division, or if you're confident enough to decompose it this way, because we know we can get the g plus kv up there, but that would need a g plus a k. We didn't get the g and the kv, we multiply by k, add the g, but we've got to multiply that also by 1 on k and subtract a g on k there, because that would get it back to v. So a little bit harder manipulation there, but you could do polynomial division and you would get that expression. So it would go in once with a remainder of g over g plus kv, which means that's going to, when we integrate it, we're going to get the minus 1 on k out the front. 1 integrates to v. That becomes a log function, g on k, log of g plus kv plus c. Now, we know when the question we're told that we have, when at the beginning the velocity is equal to u, so it allows us to get our constant, because it's a negative there, so we sub in u for that one, and x is equal to 0, so our constant is positive of that, which means we can then start to manipulate that. We haven't got that there, but we can manipulate that and get our expression for x with our constant there and that expression there. So the next part, we want to find the velocity of the particle at time v. So this time if we take our acceleration to be dv to t, so dv to t is minus g minus kv, and then it's all these ones are about taking our correct, getting something to start with that's correct. And this one's a little bit easier because dv to t gives us the minus 1 plus 1 on g plus kv, which is just going to work out to a nice log function. Then we've got t is equal to 0, v is equal to u, because that was the initial velocity. And so our constant will work out to 1 on k log of g plus ku. So t can be written in that fashion because we've got that expression plus our constant gives us the t being that one. But we also want v in terms of t, so that's the expression we wanted to get. So we start to manipulate that. We multiply through by k. By the definition of a logarithm, e to the kt would equal g plus ku on g plus kv. So we multiply across there and then start to collect our like terms. So we're able to get our terms get our expressions for v by itself and take the other things across the other side. So we're able to divide to get v by itself, and then we're able to get our expression that we wanted of g on k e to the minus kt minus 1 plus u e to the minus kt. So have a look at that algebra that's involved there. So part C wants us to get the particle, show where the particle reaches its greatest height. So we're going to have to use part B because we want the time. So the time where it reaches its greatest height. We know it's going to reach its greatest height when velocity is 0. Because once it goes right up, the velocity is going to be 0 before it starts to come back down. And that's at the point where the time is equal to capital T. So we do that substitution of T and V. So the K can multiply across and that becomes 0. So we just get the G plus Ku on G, which can be written as 1 plus Ku on G. So there's our expression that we needed to get, reminding ourselves that we get this situation. And from in D, we want the greatest height reached by that particle. Well, we know those conditions. If it's going to be the greatest height, it's going to be some point h. Again, we know velocity is 0. So from part A, we had this expression. And so we get the velocity being 0, so we do the substitution. We can multiply through by k again to clean it up. But that part becomes 0. Again, that part becomes 0. And we can look at it in this term that we get u minus g on k log of 1 plus ku on g, which is going to give us, the 1 on k there gives us the value of t from part C. So when we have a look at there, that was k there. So we can see that that's where that part comes in. So there's our manipulations that we see there that we wanted to get to. So have a look at the algebra involved. With these questions, it's always knowing where to start for your integration. So have a look and be wary of what we need to start with and then what expressions we have so we can do the correct integration that's necessary.